So let's solve the following exercise. The roots of the equation that can be seen here are non-zero integers, and we are to show that p squared plus q minus 1 squared is a composite number. First of all, let's start with a sentence or two on composite numbers. What are composite numbers? A composite number can be formed by the product of two smaller positive integers. So what does that mean? So let's take, for example, 32. 32 is a composite number because it can be formed by multiplying 2 and 16. 2 and 16, they are both smaller than the original 32, so that's why, and of course they are positive integers, that's why this 32 can be considered as a composite number. We can carry on, we can go on. This number 16 is also a composite number because it can also be produced by multiplying, for example, the two 4s. So that's why number 16 is also going to be a composite number. But what's the case with number 2? Number 2 cannot be produced by multiplying two smaller integers. It can be produced by multiplying 1 and 2. So it is not considered, they are the so-called prime numbers. Okay, and we also have to mention that number 2 is the smallest prime number. Number 1 is neither a composite nor a prime number. But let's forget, this is going to be important later on. Let's carry on, let's turn our attention and let's go back to the exercise itself. Okay, this is a power equation where the highest degree is 2. What comes to our mind? I think the first one that comes to our mind is the solution formula. I think everybody knows that. And the second one, it is the so-called Viet formulas. What are these Viet formulas? They are to find connection between the coefficients and the roots of the equation. Here, the coefficients are p and q, while the roots, well, they should be x1 and x2. What is this connection? Okay, here the connection is p equals minus x1 plus x2, while q is the multiplication of the two roots, that is x1 times x2. Okay, let's get rid of these p's and q's and let's use x's instead of this p and q. Okay, so let's substitute x1 and x2 instead of p. So we will have x1 plus x2 square plus x1 times x2 minus 1 square. Let's do the squaring. Here it is the first one, and this is going to be the second one. That's okay. Let's have a look at this expression. Let's simplify this. Somewhere in the middle there is 2 times x1 and times x2 and minus 2 times x1 times x2, so they can be deleted. If they end up, they make 0. Okay, so this is what we are having right now. Good. Let's have a look at this expression again, and I suggest that we should do some factoring. We can factor x1 square from the third item and the first item of this polynomial. If we factor x1 square, then we will have 1 plus x2 square plus the remaining is just simply copied x2 square plus 1. We can also notice that we can do another factoring here. We can factor x square plus 1 because it can be seen in two places. So if we factor x2 square plus 1, then the p square plus q minus 1 square can be written as x2 square plus 1 times x1 square plus 1. So what does that mean? These expressions here, they are all the same. It means that the first one equals the last one. And we had to show that the first one is a composite number that can be seen from the last expression, with the remark that neither of the members can be 1, because the exercise says that the roots are non-zero integers, right? If x1 and x2, they are non-zero integers, it means that the expressions in brackets cannot be 1s. So that's why they must be different than 1s. And this is how we solve this exercise.